universe, Dr. Rachel Livermore.
So thank you very much. I'm very excited to have been invited to speak to you all today. I think if we can find a way to combine astronomy and sex, we'll be laughing. For now, I'm just going to focus on the astronomy. As you can probably tell, I'm from England. I came to America just over a year ago. I drive a pickup truck, and I've learned to say y'all unironically, so I'm expecting my green card any day now. Thanks. So I'm going to be taking you right to the edge of the universe. My work focuses on the most distant galaxies, which we see so far away now that the light from them has taken almost the entire age of the universe to reach us. This means we're looking back in time, obviously the further away we look into space, and with new telescopes and new surveys, we're now probing right to the edge. So that's what we're going to do. We're going to dive right in, and we're traveling away from the Milky Way, many, many, many times the speed of light. What you're looking at is galaxies, all of them. Every single point you see on this screen has hundreds of billions of stars in it. And as we go further away, you see that the galaxies change. We've lost all our nice spirals and pretty shapes. They've gone bluer. Blue galaxies tend to mean they've got more young stars. So this is when stars were forming really, really quickly. We're over halfway back to the Big Bang now. You can see that they're all a lot smaller. They're irregular. Part of this effect is just that obviously as we go further away, our resolution isn't as good, but also galaxies are intrinsically smaller. They're starting to build up their stellar mass. And as we go further away still, you see they're not as blue as they were. They're starting to get a bit green. And this is one of the things I'm going to talk about. The fact that the universe is expanding means that the light from them becomes redder. So slightly redder than blue is green, trust me on that. And here they're now starting to look a bit orange. And if we get all the way to the back, these are the things that I study. They're tiny, tiny little red points. These are the very first galaxies that formed in the universe. And this is what's going to teach us about how our own galaxy, the Milky Way, came to be. So here we are now back at the Big Bang. There's nothing, there's no light, no stars and galaxies are formed. So that's my talk. I thought I'd just for the sake of it, I'm just going to preempt the first question. So I just stated as fact how far away these galaxies were. And in fact, to make that movie, I had to plug in a distance for each one of those galaxies and then fly through them. So how do I actually know? This is a really non-trivial question because we can't just go out with our tape measure. We can't plot it on Google Maps. Measuring distances to things in space is really one of the biggest challenges that we face as astronomers. And the reason we can do this is basically all down to one person. This is Henrietta Leavitt. This image was very kindly donated by our next speaker, Haley. So I'm pre-advertising her talk in advance. Henrietta Leavitt, my favorite scientist of all time, did all of the courses required for a BS in physics, was not allowed to be awarded a degree because she's female. But she worked at Harvard, and her job was just cataloging stars and measuring how bright they were. The way this was done at the time, this was just photographic plates, right? We didn't have digital cameras. So they had these things that kind of called like fly swatters, that had different sized holes in them. And they would hold this fly swatter over an image of a star and measure how big the star looked, and that was its magnitude. Amazingly, actually pretty accurate. They hold up pretty well. The type of star she worked on was called a Cepheid variable, and you can see images of these at the top of this picture. They're called Cepheid variables because they vary, and they get brighter and dimmer over time. Those of you who can see the bottom of the screen, there's a little graph of the brightness as a function of time. It just looks a bit like a sine wave. It's up and down. They actually don't look much like a sine wave. I think it's a bit of artistic license. Now, the reason this was a really important discovery was that she noticed something about them that no one else noticed. And this just was because she was studying this all the time. When you do something, even if it's something really menial and repetitive all the time, you notice things that other people don't. What she noticed was that there was a very clean relationship between how quickly these stars varied and how bright they were. So the brighter stars take longer to reach peak brightness in each one of their cycles. All of the stars that she was studying were in the Magellanic Cloud. Any of you who have been to the southern hemisphere may have seen this in the sky. It's the most distant object you can see with the naked eye. It's actually a separate tiny galaxy that's in orbit about the Milky Way. The reason that's important is that means all of these stars were at the same distance from us. So the ones that she saw as brighter were actually brighter. They weren't just closer. So this is a really important relationship. It's very easy to measure how quickly something gets brighter and dimmer, much easier than it is to measure how far away it is. So this is how we calibrate distance. This work was done in 1912. Shortly afterwards, it was put to good use by Edwin Hubble, who studied this galaxy, Andromeda. Now, if you have really, really, really good eyes and are in a really, really dark sky site, then this is the most distant object you can see with the naked eye. Personally, I've never managed it. This is our closest large galaxy. It's of order the same size as the Milky Way, and it's 2.5 million light years away. Well, we didn't know that in the 1920s. Extragalactic science, what I work on, is a really, really new field. So Edwin Hubble, who now has a telescope named after him that you may have heard of, looked at this galaxy and found some of these Cepheid variables in it. And by calibrating this scale, measuring how quickly these Cepheid variables brightened and dimmed, he was able to measure the distance to Andromeda. This was a huge deal because at the time, no one knew how big the universe was, and there was this huge argument between people who thought that the Milky Way was it, and people who thought the Milky Way was just one of many galaxies. People had seen images like this for a long time, but had no idea what they were. It was completely reasonable to say that this was a star with a gas disk around it. In fact, it's billions of stars, hundreds of billions of stars. But how do you know if you don't know how far away it is? So Hubble measured the distance to this as 900,000 light years. The Milky Way is about 1 light years, so this was enough to put it way outside the Milky Way and tell us that our galaxy was an island universe, as they were called at the time. In fact, that measurement was wrong. It's actually like 2.5 million light years. But if you're dealing with people who work on the very distant universe, that is an amazing estimate. Frankly, I'm very happy if I get things within a factor of 10. So this is what gave birth to extragalactic science. It also told us that the universe is expanding. And I want to dwell on this a little bit because a lot of people get